Okay.
Bifacial PV energy yield.
So, yeah. Hello, everyone. Thank you for coming. I also want to thank RatedPower team, marketing team. Thank you so much. The event is great so far. So today we are speaking about bifacial PV energy yield assessment, so the energy calculation model, essentially. Before starting, Slido. I love Slido. It's awesome. Join the Slido page. You can join with the code. You go Google slido.com, right? You join with the code, or you can scan the QR. Drop your questions in the Slido as I speak, as I go. First slide, you can drop a question right away. It's fine. You can also upvote questions from people. So if you see an interesting question from someone else you would like me to answer, please upvote the questions so that I can see them. Okay, I will also show this at the end, so if you don't join now, you can join later. So anyway, let's see. There. So we have 4 parts today: introduction, state of the art, the calculation model itself, and RatedPower results. So that's energy report and how you can use the calculation model. The intro. I first wanted to speak about the history of bifacial modules because I feel that as the utility scale PV industry, right, we only gained awareness of them in the past, I don't know, 10 years, something less than that maybe. But they have existed for a long time. The first bifacial modules were used in space applications. In space, of course, watts per kilogram is what matters the most because rockets are expensive. Sending stuff to space is very expensive. So you want as much power as you can for every kilogram of payload you send up. So people realized that bifacial modules were better for space applications really quickly, and they used them very early. As you can see, we only got the first utility scale applications some 10 years ago, more or less. And I think that market dominance came after maybe 2020, something around then, perhaps a bit earlier, perhaps a bit later. It depends on the market, of course, but it's a relatively recent thing. So let's see. There. I really like this chart. This is part of the trends report that we compile every year. It shows what I was saying about market dominance as we observed it from the point of a PV software company, right? We track the usage of pvDesign of RatedPower very closely. And we released bifacial modules in 2019 in a very basic form with only layout. 2020, we released a bifacial calculation model for the energy calculation. And you see that the increase in usage has been very steady over the years. And at some point, it gained majority. And in 2023, 90% of all simulations in RatedPower are using bifacial modules. It's also important to note that RatedPower is for preliminary design, and so we are kind of ahead of the installation market in terms of adoption trends, in the sense that people use RatedPower to evaluate potential designs, right? But it's still very remarkable, like how quickly it happened, right? The adoption was very quick. Let's see. There. So bifacial cells themselves, they are not really that different from ordinary PV cells. Essentially, we remove the back part, the back face of monofacial PV cells, right? What's interesting is that there was a time where this wasn't so easy to do due to the technology of the time. And then with PERC PV cells, this became much easier and almost natural in a sense to do. And so, as you can see, it's just removing the back face, and you have a bifacial cell. Another interesting point, which will become important later, is that the PN junction in the PV cell, it's the same PN junction, it's the same piece of silicon. We are not changing that. And that will become relevant for the modeling part later. And so, yeah, the reason for this session, there are several challenges when modeling bifacial PV plants. The first is albedo data. There are several different sources. There are many things we have to consider, and it is super important, as we will see later. We also need new design parameters, which we weren't considering or weren't as important before. For example, the height of the structures above the ground. That's not something that we were considering maybe so much in monofacial modeling. It's super important for bifacials. Of course, we have to consider the calculation of the backside irradiance itself. That's the most complicated part. And then there are other effects, such as bifacial mismatch, which are really difficult to quantify nowadays, but we have some tools to do that. And finally, a consistent challenge in energy modeling is validation data and, well, lack of validation data, really. Like, we don't have any. So that's a difficulty that we face with every new development, every new model, that we really need more data. Also, call to people who have data, please share it, make it publicly available. There is precious little real-life data available online that we can use. So this is something that is constantly making things difficult for us. So, state of the art in bifacial modeling. Let's see if, there we go. State of the art. So this is state of the art of yield calculation models for bifacial PV, right? So there, okay. So 1980 to 2000s, first space applications, like I said, also early prediction models. They were usually predicting very high bifacial gain. Then what happened between 2000 and 2012 is that the industry was using back surface field modules. The back face was completely covered, and this technology wasn't really suitable for PV. For bifacials. And when the PERC technology became dominant, right, bifacial models became much easier to produce, and that started sparking industry interest again. The first Bifi PV workshop was in 2012, and that gathered many industry specialists. There were a lot of papers at that time. If you start searching for papers for bifacial yield, right, there is like a spike in the papers we find online at that time. 2017, PVCist released a bifacial calculation in PVCist, right? And we also find a paper by Enrel describing the view factor model, which is what I will explain later. And 2020, I think it's another important year because bifacial radiance was released, and that's a ray tracing model for calculating bifacial production. And it also sparked a lot of industry interest, new papers, new research into it, which was super interesting. Okay, so early models, this started happening in the 80s. It's interesting because it happened here in Spain. There was a company in Spain manufacturing bifacial PV modules, and there was a research group in the Universidad Politécnica de Madrid doing research on bifacials, and they released papers and they released models. They were usually predicting very high bifacial gain, so it was kind of a thing saying, look, there is potential here, right? Like there is potential for a lot of production in bifacials. Then there were also some papers when the first large-scale PV plants appeared. So the plant in Japan is very well known, apparently. 20% bifacial gain observed there. This is the kind of results that get people moving, right? Like get people thinking this is worthwhile. So I think it's important. But there was kind of a hiatus, right, between 2000 and 2010 where nothing really happened, I think. And it's interesting. But essentially, eventually things started moving. And with PERC technology, more interest appeared. And yeah, so the first models that really kind of get widespread adoption are, if it loads, biofactor models, that's it. So biofactor models, they've been known for a long time, but they became more widely known with the Enrel paper in 2017. I will speak about it in detail later, so I won't get in depth here, but they are like the first models which allow us to get good results which match real-life results very well, right? That's not so easy in energy validation, but these models do give us that capability. Software examples using biofactor models. Let's see. Oh, yeah, I skipped a slide. I'll go back. We have pvCist, RatedPower, System Advisory Model, so SAM. Bifacial biofactors, that's from the Enrel. and Solar Farmer just for the backface. So there are several industry softwares using this. Of course, I think it's super relevant that PVSys uses this model as well, so it's essentially what everyone is using, right? In terms of pros and cons of view factors, sorry, can you go back, please? Another one. See. There. Okay. So pros and cons of view factors. Why did they get such widespread adoption? I think that really they are simple. That's the summary. It's not such a complicated model. They are simple mathematically. They are very fast, so computationally cheap, right? That's also not something which is super common. And they allow us to consider some moderately complex effects, especially regarding the geometry of the structures, the position of obstacles, etc. What we can't do with view factor models, and this is super important, we can't model terrain effectively, and that's a difficulty. There is no easy way to incorporate terrain into view factors. And also, I will explain a little later, but this is a 2D cut of the 3D plant, right? So it doesn't consider the effects looking towards the sides. So in this case, coming out from the screen, we can consider the edge effects, we can consider if this is the last structure in a PV plant, we can consider that, right? It's like an infinite field going either direction, so going in the pitch direction, in the axle direction as well, it's infinitely bigger. And that means that for some examples, for small PV plants, for example, we may be under-evaluating irradiance with these models. So, yeah, so for example, view factors. Next, the other kind of calculation models we have today. Ray tracing models. So, ray tracing models, this is bifacial radiance, what I was speaking about earlier. Ray tracing models are kind of the next generation model, at least in terms of complexity compared to view factor, they are like the next step. Ray tracing is a lighting simulation technique where we simulate individual rays of lights, essentially bouncing around in a 3D scene, right? Then if we combine ray tracing with path tracing, we can get a physical model. Path tracing is where we incorporate physical equations into a ray tracing system, right? So ray tracing plus path tracing gives us physical lighting simulation. We need to do some additional techniques to fix the computational cost of these systems. Essentially, we use statistical methods to reduce the workload of the system. It's kind of like we evaluate just a few rays instead of every single ray in the scene, and then we use a statistical method to figure out what we are missing, essentially. That's the Monte Carlo part. And I like this picture a lot. It shows so the different stages of noise in a path tracing system. The top one has a lot of noise because it is evaluating a very small number of rays. And as we increase the number of rays that we are evaluating, we get less and less noise, and eventually it's kind of like a perfect, smooth ball surface, whatever, right? So you see that this needs a lot of tweaking, essentially, and complicated denoising algorithms and stuff to fix the results. But they are really accurate, is what we liked about them. And they are also agnostic in the sense that they don't care about the shape of the objects, they don't care about the shape of the 3D scene. There is no infinite PV plant simplification in them, right? So we like them a lot. Let's see. So there are several examples using ray tracing, but it's kind of difficult to actually use it in a practical a practical use case today as a PV developer or as a PV engineer. We have bifacial radiance. Then we have PVKCL, this is in ray tracing as well, although there is very little information regarding exactly what they are doing. Then we have some implementations by some companies. I feel like really the most interesting thing that we can get with ray tracing today are like one-off studies. So for example, Soltec, they analyzed the effect of the torque beam using bifacial radiance, and they gave us a shading value that we can input in PVSys. And people have been using bifacial radiance for a few years now also to evaluate the position of sensors, to evaluate the effects of different parameters, and it's all really interesting. And you can see in that picture the depth of the model, right? You can actually evaluate individual cells in the structure, and you can model the physical properties of the torque tube and how much light it reflects. And so, there is a lot of potential there to do some very complicated simulations, right? But it's super computationally expensive. It takes hours to run these kinds of simulations. So, finally, we arrive at the calculation model that we use in RatedPower. It's a view factor model, but it's a bit different than what we find in other examples. So let's see. The first part of the model, there we go. So ground reflection, albedo. Albedo is super, super, super important. I can't stress this enough. If your albedo is wrong, your entire bifacial simulation is wrong. The reason is very simple. That chart shows bifacial gain in the vertical axis and albedo in the horizontal axis. And you can see a straight line, right? That means it's proportional. More albedo results in more bifacial gain. So it's super important that you get your albedo right. There are several different ways to get albedo data. You can use satellite sources. That's the most commonly available, easy to get information. Ideally, you would want to have a pyranometer on field, but that's more difficult, right? It's also important to keep in mind that when we use satellite albedo, we are looking at the albedo values over a long historical period, say 20 years or something, right? However, when we build a PV plant, we usually disturb the ground, right? Like there are machines moving over the ground. There may be a bulldozer moving earth, and all of that changes the characteristics of the ground, and it changes the albedo. So that means that even our satellite data from 20 years ago may be very different when we actually get to build the PV plant, right? And this is something that we need to consider. Satellite data gives us natural ground albedo, right? The state as it was before we built the PV plant, it may be different afterwards. This is a reason to adjust and to use your own data from operational PV plants to improve these estimations, right? The basis of all view factor models is what we call configuration factors. Configuration factors, it's something that comes from the, thermal modeling, so thermal engineering. And the concept is really simple. What we are doing is that we want to calculate how much irradiation one surface perceives coming from another. So in this case, let's see if I can use this. So you can see that part there, that's the surface we are evaluating. And this would be whatever is emitting irradiation, right? And these are the angles that we see in this equation here. So theta 1 could be this one, and theta 2 could be this one, right? This was used initially, imagine you are calculating the thermal characteristics of an oven, right? The kind of oven you have at home, and you're evaluating how much heat your pie is getting, or something like that. This is what this technique was used for. But now we use it to evaluate irradiation in an open environment, right? So if we translate heat to irradiance, we are looking at how much sky we are seeing from some point of the ground, and we are also evaluating how much ground the structure sees, right? And how much irradiance comes from those sources. So the first evaluation we need to make is the one that's coming up right now. There we go, irradiance perceived by the ground. So this is the first thing we need to consider. Bifacial production rates come from reflection of the ground. So we need to evaluate how much irradiance the ground sees, right? We already know the albedo of the ground. The albedo is uniform throughout the entire ground, right? But we need to know at this point how much irradiation we are perceiving from the sky. So first component, beam irradiation, so direct sunlight. It's super simple to evaluate. We just look at whether or not some part of the ground is under shade or not. If it's shaded, then the contribution of the beam irradiation is 0. Diffuse irradiation, it's a bit more complicated. We need to use view factors, and this is the first step where we are actually using view factors for something. This is our patch of sky we are seeing, and these are our angles, right? And we are evaluating how much diffuse irradiance we are getting at that point from the sky. It's important also to know that the irradiance here, it's not any irradiance value. For the beam irradiation, we can use the beam horizontal irradiation, of course, because it's measured on horizontal ground. But for the diffuse irradiation, we can't use diffuse horizontal irradiation because we are only interested in the part of irradiation that comes from the skyvault. So to do that, we use the Pérez transposition model, and usually you transpose to a tilted surface, but you can also use the model at a horizontal surface, right? And the Pérez transposition model separates the diffuse irradiation in 3 components, which are the circumsolar, so the corona of the sun, the sky vault itself, and the horizon profile. So we take only the sky coming from the sky vault, the irradiation, sorry, coming from the sky vault, right? And that's what we evaluate. Here come the first quote-unquote implementation challenges in view factors. So you saw that the configuration factors calculations is super simple, but actually implementing is a bit more difficult because this scene we are evaluating here, we may have any number of structures, any kind of geometry, structures may be closer together, more separate, higher, lower, whatever, right? We need to consider all that, and we need to evaluate as many patches of sky as possible, because otherwise it's going to be inaccurate. So that's one difficulty, right? So this is to evaluate how much irradiance the ground perceives. Then we need to calculate how much irradiance the structure perceives, the back face of the structure perceives, right? So we apply the albedo, of course, to the value we obtained earlier, and we get reflected irradiance. That's cool and all, but now we want to know how much of that irradiance is actually reaching our back face, which is that point over there. And so you will notice that I quoted the rays part in this slide. I don't want you to think that this is any kind of ray tracing or ray casting or anything like that. It's not. This is just what I used to explain it. But essentially, we are starting from this point. We are casting a bunch of rays all over the place, say 1 ray every degree, right? So 180 rays. And at the intersection of the ray with the ground, we evaluate how much irradiation the ground is reflecting, and then we multiply by the configuration factor of the slice. So you see that we are doing like 180 configuration factors, and each different ray we evaluate has a different irradiation value. Why does the irradiation on the ground change? Because we have shades, because we have angles, right? So this ray, for example, is contributing way less than this ray, for example, because of the incidence angle, right? Also, at this stage, we incorporate the near shading objects. So that is the torque tube over here and the near structure over here. And so rays which are obstructed by near structures aren't considered. Finally, you will notice that we are only getting green contribution from the ground, and we are not getting any contribution for the structures. We are neglecting reflections coming from the structures behind. The reason why we do that is that first, it's very easy to it's very hard, sorry, to model how much reflection that's going to be from the modules behind. Second, PV modules are supposed to absorb energy and absorb sunlight, so there shouldn't be much energy coming back, right? And we want to keep the energy balance correct. And third, modules have things like anti-reflection coatings and different glass properties, which would also be very difficult to model. So we neglect them, and it's mostly fine. Yeah, so we are only considering irradiance coming from the ground. Finally, more contributions to the back face. We have the sky itself. So the module can see parts of the sky, maybe a small sliver, right? But it's something we have to consider. Also, maybe you are doing a fixed structure design, and perhaps in some days of the year you can actually see the sun from the back face. We also consider that. But these are very small contributions. Also very important, as you can see in the picture, modules tend to have some degree of transparency. That can be considered. The way we consider that is that when a beam irradiance ray is blocked by the structure, we don't remove all the irradiation, but part of it. Say only 3% passes through, right? So instead of losing all of the irradiation, we only lose 97%. Also very difficult to model. It's kind of a thing which may increase your bifacial gain and artificially, so it's something to be careful about. Yeah, so finally, after all of this, we still don't have effective irradiance on the back face. We need another step. We need to evaluate the back face irradiation at several points along the table. So say here, 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 and here. So it's kind of like we are integrating the radiation along the table, right? Why do we do that? Because I have a picture in the next 2 slides, I think, but back face irradiance is actually very heterogeneous. It's not consistent, it's not constant at all, right? We want to find kind of an average which is representative of the entire thing, and that's why we are evaluating at several different points. Additionally, 2P trackers, for example, they have the torque beam gap, right? Like the modules are separated at the torque beam, and that means that it doesn't make sense for us to evaluate right above the torque beam. So we need to evaluate just before and just after, right? Otherwise, we would be decreasing the irradiance perceived by the modules, which isn't actually happening because they are not there. So in other words, we need to evaluate just in the positions where the modules actually are and not anywhere else. Yeah, also soiling gets applied at this stage. That's super important too. We have back face soiling. That's something that may happen. Yeah, then the electrical model. So really, what I said earlier about you remember that I said that we have the same piece of silicon being irradiated? That simplifies things a lot for us. Because all we need to do is take the traditional one diode model and plug in the additional backface irradiance into the model itself. That's a relief. Like there is one part of this modeling which is super simple, which is this one. The important part is the bifaciality factor. So you probably have heard of this value. Bifaciality factor, it's a D rate on the backface irradiance, which actually produces electricity. It comes from the fact that PV cells are not symmetrical in the back face and in the front face. One of the most normal things we find is that the number of bases, of aluminum bases in the back face is different than the front face, and there are more of them. So we lose more light due to the aluminum bases than in the front end, and we need to consider that. And there may be other effects as well. This information is actually in the PAN file, the bifaciality factor, and it's usually somewhere between 70 and 90%. It varies depending on the technology. For example, heterojunction modules have higher bifaciality factor, which is a nice advantage of the technology, right? Yeah. So then we have effective irradiance, we have the electrical model, we have the production of the bifacial module in electrical power, right? So there are some final losses that we need to consider. One of them is bifacial mismatch. As I said earlier, the backface irradiance is not very homogeneous. You can see that here, the top value is 1,559, so then we have 1128 over here, and there is a significant difference. And that's front plus rear, right? So here we are adding up them both, but the gist of it is that there are significant differences, and that causes a very small proportion of mismatch in the back face. The way we consider it is that it's a fixed D rate, which is only applied to the back face irradiance. And this is something that people don't always get, but essentially, if you set an electrical bifacial mismatch value of, say, 10%, that's 10% of the backface production only. So if you have 5% bifacial backface production, it's 10% of 5%. So it amounts to a really small loss, but it's still something that we need to consider. And this is also something that you should consider changing depending on your type of structure. So for example, structures which are very high off the ground will have less electrical mismatch. Fixed structures will have less electrical mismatch, but 1P trackers will have the most electrical mismatch because the bifacial cells are right over the torque beam, right? And so they will have kind of like a shade right where they are. So that's something that you need to look into, right, when assessing different structure options, which is that this value may change between them. Yeah, so finally, we implemented this calculation model. we think that it was a good model, right? We based it on the literature, but how do we actually validate the results? This is a complicated part of the development usually because, like I said earlier, we usually have issues finding data that we can use to validate. But there was some very useful literature. For example, this paper by the Enrail and Sandia people, it was super useful. Also, we compared to PVC simulations, and eventually we also got a report by Black and Beach, which found that the simulations were super close. But what I wanted to show you is the comparison with the paper. So the charts I'm going to show now are a comparison of our results to the results of this paper. So in this chart, we show the bifacial gain compared to the GCR. So here we have higher pitch values, so the structures are more far apart. And then here we have closer pitch, so the structures are closer together. Also important to consider, the bifacial gain calculation, it's the coefficient of front face to back face. Oh, sorry, the other way around. So back face to front face plus back face. So it includes the effect of the front face. So we are not evaluating just back face production, we are also evaluating the front face when we are looking at this. It's interesting to note that there is not perfect agreement between the models. You can see that PVC is above the Enrail models. And also here, when it says radiance, this is a ray tracing model using bifacial radiance. And you can see it right there. So yeah, the effects are fairly obvious, right? The more we separate the modules, the less shades there are on the ground below the modules, other than the shade cast by the structure itself. And so we have higher backface production because of that. The next chart is related to the clearance. So clearance is the height above the ground of the structures. And I think this one is a very interesting chart because it shows that there is a point where it doesn't make sense to increase the height anymore because you're not getting anything out of it, right? This is another thing that you may evaluate for your own designs. Of course, as long as you're not running into excessive mechanical stress, right? Because at the end of the day, you're making the piles longer, it will have an impact. But you can get more production by increasing the height. And as you can see, it's actually significant. Going from 0.2 to 0.3, we get a jump of 2% maybe. So it's a lot. These values of bifacial gain, by the way, they are kind of high. That's because these simulations were done using bifaciality factor of 100%. So we are not losing anything due to the module itself. What I mean by that is don't focus too much on these values, focus on the trends, right? The trend is what matters in this case. And you can replicate the trend using the RatedPower software as well. It's perfectly doable. Yeah, so finally, results. How do we look at results from the RatedPower simulation? The energy yield calculation model has a primary goal, which is to calculate the production of a PV plant. But it has a secondary goal in that we want to evaluate the quality of the design as well, and we want to help the decision-making process of improving the PV plant, right, and finding issues with our design. So two traditional examples are the module temperature, right, and the inverter power limit. As you all know, inverter power limit probably indicates excessive DC-AC ratio. Module temperature loss, if it's too high, perhaps we need to look into our meteorological data, right? So these are things that we look into. We also had that goal in mind when we designed the bifacial calculation model, and we implemented some reporting systems, right, that allow us to evaluate the quality of the design in terms of the bifacial part of it, right? So the first values that I want to highlight are the bifacial gain. You can find that in the energy report in the table 17. It's right there. We also have the albedo that we use. This is super important if you are going to replicate values in some other software. I also like to highlight the performance ratio because in RatedPower it can go above 100%. That happens because the PR is calculated by comparing production versus theoretical production using front-face irradiance. That's according to a standard from a few years ago. we probably should change this by implementing the newer standards which consider backface irradiation. But then we would have two performance ratio values, which is a bit confusing, so we still haven't done that. It's not such a big deal, really. All you need to know is that it can happen, and it's fine. It's due to high albedo mostly. Also, like, in order to get this value, I had to simulate with like 60% albedo, so this is not something you will find easily unless you're running some very extreme scenarios. The more interesting aspect of our bifacial reporting is actually, let's see, there we go. So the bifacial losses that we show in the losses table. So we have two parts here. The first part is these three losses. To be perfectly honest, these are kind of made up in the sense that these are not using the configuration factors, the view factors model. We are just taking albedo in this one. This is straight albedo. And then for this one, we are using the transposition models to compute how much irradiance would reach the backface without any kind of shading or effects at all, right? Just the ideal value on the backface. Then this value here, effect of ground shades, this is where we are actually getting results from the view factor model. This result is calculated without considering any of the near shading objects. So it's just the structure itself and the ground, but the ground is already with the shades coming from its own shade and the shades of the structures behind it, right? So we see a very high loss value in here. This loss is theoretically 0% if the structure is perfectly transparent. Of course, that's not the case, so it can't ever be 0%. But for example, if we reduce the GCR, so make the structures further apart, this goes down because the shades are further apart from the structure and you get more irradiance coming back to the backface. We also have far shadings. This is mostly just the beam irradiance getting blocked. We have near shadings. This is torque beam and the structure behind it. Tilt has an impact on this one. Pitch has an impact, of course, and also the shape of the torque beam and the kind of tracker. So 2P trackers will have a lower near shading value than 1P trackers at the same GCR. And then we have soiling and incidence angle modifier. So essentially the goal with these losses is to help you assess if there is anything you could improve in your design. Right? Still not super straightforward, but there are some conclusions that you can draw from this. And also running different analyses, you can actually see the impacts on these losses, which can also be helpful, right? Also, the incidence angle modifier loss tends to be, I will speak out it anyway. The incidence angle modifier loss tends to be high for the backface. That's because the irradiance is mostly isotropic, so it comes from all directions, so the incidence angle is pretty bad, and we lose a lot of it due to the incidence angle modifier. This is something that PV6, for example, doesn't consider. And I hesitate about it sometimes because it's possible that it's included in the bifaciality factor, but we don't know. We don't know for sure. So we include it in our model, but it can be removed if necessary, right? So anyway, there are more losses after electrical conversion. We have the bifaciality factor itself quantified here. This will, of course, be proportional to the bifacial gain. And we have bifacial mismatch as well. These losses will counterintuitively go up if you have higher bifacial gain because they are proportional to the backface production, right? So if you have higher backface production, these losses will be higher as well. So that's something to keep in mind. Nothing wrong with that happening. It's just that you are having more backface production, and so your losses due to backface effects are increasing. Also, the temperature loss doesn't change with bifacial modules. It's something you should keep in mind as well. It shouldn't change, but it's something that we keep an eye on as well in terms of modeling. Like, should we be considering this differently? Maybe should the thermal coefficients be different, right? When we are using thermal coefficients calculated for monofacial modules, the dissipation of heat may be different when the backface is a piece of glass instead of a plastic backface or whatever, right? So it doesn't change on its own. Perhaps you should look into it in more detail. So let's see. Finally, inputs to keep an eye on. The minimum ground clearance, so this is the clearance from the ground, higher clearance, higher bifacial gain. The back face incidence angle modifier model, the default option is conservative. You may want to change it to the manufacturer incidence angle modifier profile, which is usually less conservative, and albedo, of course. In RatedPower, we have satellite sources by default, which you can use. We have MODIS and NASA Power. They include the effects of seasonality. So imagine you are in a snowy location, it will show in the albedo values, which is useful. And you can also input your own albedo values. So yes. And finally, let's see. Yeah, so this is the end of the presentation. We have a very in-depth methodology for the calculation model. You can download it from the knowledge base. You have equations, sources, so references, and detailed model descriptions in there. I encourage you to go look into that if you are interested in knowing more about the model, and especially the bibliography is super useful as well, like tracking where we got the models themselves. So yeah, that's the end of the presentation. So I have 4 minutes, which is less than I expected, but it's time for questions. So yeah, I think it's time for the questions screen, right? Oh, it's there. Thank you. Cool. Okay. So first question, does the shading in the back affect the frontal circuit, or are these completely separated? I guess you mean in the sense that the back face shades affect the production, and the answer is yes. We sum up, we add up the frontal irradiance to the back face irradiance to get effective irradiance. So if there is more back face shading, we are getting less overall effective irradiance, and that will have an impact on production. And that is not affecting the frontal circuit specifically, but in a way it is. Then, does mismatch and soiling in the back affect the front also? No, they are separate effects completely. We have front soiling and back soiling, and we have the global mismatch value, which applies to all PV module production, but we also have the back face mismatch or bifacial mismatch, which is only proportional to the back face production. Will RatedPower implement a triple rail mounting system, one more rail in the middle, and consider its effect on bifacial gain? That's an interesting suggestion we haven't considered. Mr. Anonymous, please let me know later so that we can learn more about this proposal. Right now, it's not in the roadmap. I can tell you that much. Then in the bifacial gain graph showing comparative values, what kind of mounting system was it? Yeah, it was a landscape system, one landscape, experimental system in Albuquerque, I think it was. And it was like very small rows. And they were comparing with measured values as well. And so it was an experimental installation. They were comparing measured values versus several models and plotting those charts. Can we expect ray tracing bifacial calculations in pvDesign, or will you stick with the view factor method? Well, we are developing a ray tracing model. We are also using ray tracing for the back face as well. Can you expect it? I hope so. I don't have any release dates, so we are working on it. We feel like it's probably the best model for considering terrain effects, and that's not something that we get using any other model. So that's why we are developing that, but it's going to take some time still. Which are the best data sources for albedo? Well, the answer is simple, in my opinion. You get a pyranometer on the ground. That's the best possible source for albedo. Even then, you have to consider that the ground may be heterogeneous in the PV plant, so you may have different patches with different properties. You also have to consider that the ground may change. Other than that, if you're looking at satellite sources, I think SolarGIS is very good. Like, their methodology is sound and it's very well documented. So I would look at SolarGIS data if you want like good quality satellite data for albedo. The automatic albedo sources we have, which are MODIS and NASA Power, they are really good because they are publicly available worldwide data sets, free of charge, right? But I would expect SolarGIS data to be better than that, even if it's using, I think that SolarGIS is actually using MODIS data as well, but they do additional processing over that, which may improve the quality of the data. And also, at the very least, they can tell you about uncertainties, which is not something that is easy to find for the public sources. So yeah, 30 seconds left. So thank you so much. I hope you enjoyed it.